It's me, Linus. Hope you enjoyed the last video. Thank you so much for your support. In this video, we'll be discussing last year PYQs from the topic of coordination chemistry and D and F block elements of grade 12 chemistry CBSE board. Okay, so let us start with the first question. Explain why FeCN6 is an inner orbital complex, whereas FeH2O6 is an outer orbital complex. Okay, so FeCN6, right? Yes, in the case of FeCN6, what is oxidation state of Fe is oxidation state of ion is Fe3 plus, right? That means Fe is 3D64S2. That means Fe3 plus is 3D5. Okay. Okay. So here Cn minus 6 coming. Okay. First one is FeCN6 3 minus. And in this case of Cn minus, where the electrons are sitting like 1, 2, 3, 4, 5. Okay, and 4s is vacant. Okay, 3d5 4s. Okay, now you see here Cn is coming, right? Cn is a strong ligand, Cn minus is a strong ligand. So what will happen? Pairing occurs. Pairing will take place, and we will be getting what? 1, 2, 3, 4, 5. Okay, one unpaired electrons will be there, and the Cn minus will come and sit like this. Okay, 1, 2, 3, 4, 5, 6, 7. Yes, so the hybridization will be D2sp3 hybridization. Okay, D2sp3 hybridization. That means because of the strong ligand Cn minus, pairing occurs leading to D2sp3 hybridization. Okay, and in the case of H2O, ion is also 3 plus, but H2O is what type of ligand? It's a weak ligand, right? Weak ligand. So there will not be any pairing of electrons. Okay, so its hybridization will be what? Hybridization will be yes, P3D2 hybridization. So in the case of FeH2O 3 plus. Okay, so that means in this case N minus 1 d orbitals are using, and in this case Nd orbitals are using. So that is inner orbital complex. So FeCN6 is using an inner orbital complex, and FeH2O6 plus is use 6 FeH2O6 bracket 3 plus is using in outer orbital complex. Okay, so this is the, so what you have to do is you have to find out whether the ligand coming is weak or strong. So if it is a weak ligand, there must be pairing should take place. Okay, and in the case of weak ligand, there will not be any pairing occurs. Okay, yes, let's move to the next question. CrNH36 is paramagnetic, while nickel CN4 2 minus is diamagnetic. Okay, okay, let us do this. Ammonia is a weak ligand, right? CrNH36 3 plus Cr, and ammonia is a weak ligand, so Cr is 3 plus. So Cr is 3 plus means it is having, Cr is having, what is the electron configuration of Cr? 3d5 4s1. So 3 plus means what? 3d3 will be the electron configuration of Cr3 plus. So it will be what? It will be existing like 1, 2, 3, 4, 5, 3 electrons here. Okay, and in the case of nickel, yes, NiCN4 2 minus. Yes, nickel is in which oxidation state? 2 plus oxidation state, that is 3d8. 3d8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. And Cn is coming, right? So what will happen? Here pairing will take place, right? So paramill takes place. So 3D8 will become what? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. And here who will come? Cyano group come 3D, 4S. Then next will be in P, right? P2. So hybridization will be DESP2 hybridization, square planar geometry. Okay, square planar geometry. But in the case of CrNH36, here there is no unpaired electrons. No unpaired electrons. No unpaired electrons. So that means it is diamagnetic. This is diamagnetic. In the case of CrNH360 plus, who is coming? Ammonia is coming, right? NH3 is coming. It's a weak ligand. So there is what? There is what? There is 3 unpaired electrons. You can see there will not be any pairing takes place. So what will happen? This is a paramagnetic complex. Okay. Yes. Moving to the next question. Predict which of the following will be colored in aqueous solution and why? Okay, which of the following will be colored? So coloring depends upon the number of unpaired electrons. Okay, and if unpaired electrons is present, what will happen? Unpaired electrons is present, what will happen? DD transition will take place. DD transition. So that means color. That is the reason for color. Okay. So scandium 3 plus. Scandium is 3D14S2. Scandium 3 plus means what? 3 plus means 3D0. There is no D electrons, right? There is no D electron. Sorry, there is no unpaired electrons and D electrons also 0, right? Yes. Next is iron. Iron is 3D64S2. As atomic numbers are given. Okay. Iron 3 plus means what? 3D5. So there are 5 unpaired electrons. Okay, 5 unpaired electrons. Yes, of course. In the case of zinc, what will happen? In the case of zinc, Zn2 plus, right? And zinc is 3D10 4s2. Zinc 2 plus means 3D10. So completely filled d orbitals, right? Completely filled. So that means here unpaired electrons is having for only Fe3 plus. So that will show the color property. Okay. The other ones, which is scandium 3 plus, it's having no d electrons, and Zn2 plus, the d orbitals are completely filled. So DD transition is not possible in both of the cases. So Fe3 plus, it is having 5 unpaired electrons, will show colored compounds in aqueous solution. Okay. Yes. Let us move on to the next question. Why do transition metals and their compounds show catalytic property? Okay. Why? What is the reason for they are showing catalytic property? These transition metals are showing catalytic property. What will be the reason for that? Yes, transition metals, right? That means, yeah, yes, because of the absence of d orbitals, right? Next question is, why do transition metals and their compounds show catalytic properties? So we know transition metals are having, they show variable oxidation state, right? Yes, transition metals show variable oxidation states. They show variable oxidation states and they take part in what? Complex formations, right? These transition metals provide larger surface area. Okay, provide larger surface area. That is why they show catalytic activities. Okay, yes. Now, next question is, what the formula of the coordination compound? So, it is given, IUPAC name is given. You have to write down its formula. Okay, first is potassium. So, that is a positive ion. Potassium is the K. Wait, for tetrahydroxidozingate. Okay, tetrahydroxidozingate. So, how will you answer that? Tetra means 4, right? OH4. Okay. Zingate means what will be the metal is zingate. Tetrahydroxidozingate. Okay. So this is the thing. And what is potassium? How many potassium atoms should be there, right? So OH minus, it's a minus, right? 4. 4 minus is there, right? 4 minus, right? And zinc, potassium is zingate is 2 plus, that is given. Zingate is 2 plus. So here, what will be the charge of this 2 minus? 2 minus charge. So that the zinc will become 2 oxidation state. Okay. So you have to remove that 2 minus by putting a potassium here. K2 ZnOH twice. Okay, K2 ZnOH twice. Yes. Arrange the following complex in the increasing order of conductivity in their solutions. So conductivity depends on number of ions, right? So what you have to check is how many ions are possible for these compounds. Okay. So the first compound you can see here, Cr, yeah, CrNH3 5Cl, that is one ion, and 2 Cl minus ions are the 2 Cl minus ion plus CrNH3 5Cl 2 plus. So total how many ions? 3 ions in this form. So here there is nothing outside the counter ions. There is no counter ions, right? No ions outside the square bracket. So there is only one. Okay, one ion. And here what is how many number of ions here? 3 Cl minus ion plus CrNH3 6 3 plus. Okay, so 3 plus 1 4 ions. So what will be the increasing order? First will be this, second one, then 3 ions, then 4 ions. Okay, that will be the increasing order of their conductivity. So which is more conductive? This will be the most conductive because it contains 4 ions. Okay, now identify the type of isomerism exhibited by the following complex. Okay, so CONH3 5NO2 2 plus. So we have 4 different geometrical isomerism and structural isomerism and geometrical isomerism and optical isomerism also we have. And in the case of structural isomerism, there are 4 different types of structural isomerism are possible for coordination compound. Ionization isomerism, linkage isomerism, hydrate isomerism, and coordination isomerism. So in the first compound, when you see very carefully the first compound, you can see a NO2 group, right? NO2 ligand. It's what is the importance of this NO2 ligand? Yes, it is a ambidentate ligand, right? Ambidentate ligand. Whenever there is ambidentate ligand, make sure that it is possible for exhibit which type of isomerism? Linkage isomerism. So first one is linkage isomerism. First one will be X. What about the next one? Next one is COEN thrice Cl3, right? That is COEN thrice 3 plus. Okay, so for this coordination compound, it's a EN. EN is what? EN is a bidentate ligand, right? So the coordination number of this will be 6. So exhibiting octahedral complexes, right? So octahedral complexes, coordination number 6. Ligands are arranged in various ways, right? When we see this is bidentate. Arrangement of ligands will be, this will show which type of isomerism? Optical isomers. What are optical isomer? What are optical isomer? Yes, they are non-superimposable mirror images. Non-superimposable mirror images of each other. Okay, so you can get 2 optical isomers for this. 2 optical isomerism this will show. Okay, so this one, when you see COEN thrice, you must remember about optical isomerism. It can show non-superimposable mirror images it can form. Okay, yes. Now it's this, how is crystal field splitting? Crystal field splitting energy for octahedral related to that of tetrahedral. Very important question, because we know in the case of tetrahedral splitting and octahedral splitting, we have studied one equation for that. The tetrahedral splitting is about 4/9 of octahedral splitting. Just write down this equation, you will get 1 mark. Okay, this is a relationship between what? Tetrahedral and octahedral splitting. So tetrahedral. So tetrahedral is less than octahedral. Okay. So octahedral splitting is okay. Tetrahedral splitting is about 4/9 of octahedral splitting only. Okay, that is a crystal field splitting energy for octahedral complex that is related to tetrahedral one. Very important equation. And what is the IUPAC name of the following complex? So let us analyze what are the ligands here. Chlorine is the EN, that is ethylamine. Okay, so two chlorine atoms, so we can write like dichlorido. Chlorido, since it is a negative ligand, you have to make it chlorido. Then two En is there, so in the case of En, you have to make it bis. And what is ethylamine's IUPAC name? Ethane. 1,2 diamine. Okay, so ligands are over. Then platinum, right? Platinum. What is this? This is a positive ligand, positive complex. Complex is positive, right? So platinum. Name of the metal should be its name itself, platinum. And what is its charge, oxidation state? You have to put in bracket in Roman letter, right? So what is that? Here it is NO3, right? Nitrate is what? Nitrate is, we know, it is -1, right? So 2 nitrate. So what will be the charge of the complex? PtCl2En twice will be 2 plus. Okay. Yes. So En is a neutral ligand. Chlorine is -2. Okay. Chlorine is -2. So how will you find this -2? And yeah. So this is X and it is neutral. So X -2 is equal to +2. So X is equal to what? +2 +2. That is equal to 4. So that will be 4. Oxidation state of platinum will be 4 in this case. And in the bracket and outside the counter ion is nitrate. So write its name as nitrate itself. Nitrate. So got the idea. First, what you have to do? You have to identify the types of ligands. And ligands are written in the alphabetical order. If more than one ligand is present, same ligand is present, you have to use di, tetra, tri, etc. And in the case of En, ethane, 1,2 diamine. If there is more than one En, so you have to use bis, tris, etc. Okay. Then after writing the metal name, you have to put in bracket in Roman letters the oxidation state of the metal in the complex. After that, the counter ion, which is negative. If it is a positive counter ion, you have to make it on the beginning. Okay. If it is potassium like sodium ions, you have to write its name in the beginning. Okay. So positive part should be named first, then negative. Here positive part is the complex. That is why I put its name. Okay. Next is write the geometry and magnetic behavior of the complex. Nickel tetracarbonyl on the basis of valence bond theory. Okay. Yes. So nickel tetracarbonyl. And carbonyl is a neutral ligand. Here nickel is in which state? Which oxidation state? 0 oxidation state. Okay. Yes. So we know nickel's atomic number is 28 and its electron configuration is 3d8 4s2. Okay. Yes. So let us draw this structure. Nickel is in 0 oxidation state. So it will be like this. Okay. S2 and P is there sitting freely. Yes. So nickel tetracarbonyl. 1, 2, yeah, 3, 4, 5, 6, 7, 8. 3d8 and here S electrons are there. Okay. 4s2. Who is coming? Which ligand is coming? Yes, it is carbonyl ligand. CO ligand is a what kind of ligand is that? Yes, it is a strong ligand. Very strong ligand. So what will happen? Yes, pairing will take place, right? And this S electrons will be moved to the d orbital. So what will we get here? 1, 2, 3, 4, 5, 6, 7, 8. It is paired and S electrons is moved to D. So S and P will be free and here carbonyl ligands will come and place here. Okay. So I'm getting the hybridization as what? sp3 hybridization. So what is the geometry? If it is sp3 hybridization, geometry will be Tetrahedral. Yes, sp3 tetrahedral. When it is dsp2, it is coil planar. Okay. And what about the magnetic behavior of the complex? See, here all are paired, right? All paired means what is the type of magnetic property it is having? So it is a diamagnetic complex. Okay, it is diamagnetic complex. Yes, moving to the next question. What type of isomerism is shown by the complex? So when you observe this complex, you can see two coordination spheres, right? Yes. So that means here exchange of ligands or metal atom can take place. So what type of this coordination complex? This exhibit coordination isomerism. Very simple. When you see two boxes and you can exchange like this, so it will be like this: COCN6 and CRNH3. So what type of isomerism is coordination isomerism? Okay. Then for the coordination compound on the basis of the crystal field theory, write the electronic configuration of D4. Okay. So in the case of crystal field theory, we know T2G, right? T2G is the configuration. So if it is D1, no problem, T2G1, EG0. If it is D2, T2G3, EG0. If it is D3, what will happen? Oh, here 2, okay. T2G3, EG0. Okay, this much is okay. After D3, there comes D4. Okay. In the case of D4, two possibilities are there. Either this electron can sit in T2G4 and EG0, or it can jump to EG like EG. T2G3, EG1. Okay. So what will happen depends upon this. Okay. Here delta 0, that octahedral splitting is less than pairing energy. So less than pairing energy means that gap between T2G and EG is less. So what will happen automatically? Automatically, the electron will jump towards which? To EG. So the in D4, in this case, it will be what? T2G3, EG1. Okay, T2G3 and EG1. Is it clear? What is happening in the case of D4 is that two possibilities are there. Either this electron can pair in the T2G itself and make it T2G4 and EG0, or what it can do, or it can jump to EG. Since here delta 0 is very less than what? Delta 0 is less. That is, that gap is very less, so electron can easily jump to the EG level, right? So you will get the configuration of this one, and it is jumping, right? So it is a what type of complex? It is a high spin complex. It is a high spin complex. Okay, hope you get it. Yes. Next is out of CuNH363 plus and CuNH34Cl2 plus, which complex is having is heteroleptic. Okay, so complexes can be classified into homoleptic and heteroleptic. Okay. Yes, like homoleptic complexes, what will happen is that there is only one kind of donor group, only one donor group. Okay, that means only one type of ligand. And in the case of heteroleptic, what will happen? More than, okay, more than one type of ligand. Then check this. Which one is heteroleptic here? More than one type of ligand is present in this complex, right? So it will be heteroleptic. And why? Because it contains more than one type of donor atoms or ligands. Okay. Yes. Yes. Next question is, why do transition metals show variety of oxidation states? Okay. So what is the reason why transition metals show variety of oxidation state? Because symbol, right? Oxidation state, because there is they are having n minus 1 d and ns electrons, right? Subshells takes part in bond formation. Okay, bond formation, and we know that both are having what? Comparable energies. Okay, comparable energies. Okay, so due to the presence of unpaired electrons in the d orbitals, okay, they show, you can say two answers. First one is this one, okay, because they are, these n-1 d and ns are taking part in bond formation and they are having comparable energy, so they show variety of oxidation state. Or you can mention the point that is, it is due to the presence of, due to the presence of what, unpaired electrons, unpaired electrons in d orbitals. Okay, yes, so this is the answer. Okay, hope you enjoyed the video. If you like the video, please like it, share to your friends and subscribe our channel, and we will be back with more videos and will help you to make good scores in the exam. Okay, okay then, bye, thank you, have a good time.